evening, everyone, and welcome to BCS Coventry's September 2025 meeting. My name is Dr. Diana Basinkantar. I'm the chair and I'm the branch chair for BCS Coventry. Our topic for discussion at today's meeting is AI in healthcare, neural AI versus symbolic AI, and why we need neuro-symbolic AI. We have 4 speakers today. I believe our lead speaker is Dr. Mercedes Aguero Castellero. We also have Apishan Tayanathan from University of Southampton, and we have Mohammed Iqbal and Sarah from the University of Buckingham. I will let the speakers introduce themselves more, and the speakers will take turns in making presentations. Thank you for coming. Over to you.
So thank you very much to everybody to join us. It's quite exciting. We decided to present the latest of our work. So some of the work is going to be presented in an International Artificial Intelligence Conference in December in Cambridge. But we decided that perhaps as we are trying to encourage people to look into neuro-symbolic AI and try to see what the benefits could be, we thought that it would be useful to share with you as a premiere the kind of work we are doing and the kind of research that we are doing. I'm delighted to say that we have 3 guest speakers, which is university students that they are working with me. I was lucky enough to be a researcher at the University of Manchester for a number of years and working for different groups. So I had the chance to move from description logic and what we call symbolic AI to natural language processing. And of course, as all we know, ChatGPT and deep learning and all these latest advancements in the field of neural networks has also been considered. So I also was lucky to be a lecturer at the University of Southampton and also a lecturer at the University of Buckingham. And I encourage my students also to participate in research. And some of them even decided to do their final year project on this. So I will leave it to my students to say a little bit about themselves. So Apishan, please.
Hi, my name is Apishan Tayanathan, and I just graduated from Southampton this July. I had the lovely opportunity to work with Mercedes in my 3rd year project, and I'll be talking about it later.
Thank you, Apishan. Muhammad, perhaps you can also say something about yourself and the work that we have been doing.
Yeah, hi, my name is Mohammed Iqbal. I also had the opportunity to work with Dr. Mercedes during our SSC project. And yeah, we did a recent research that we've just published, and I'll be talking a bit more about that later.
Okay, thank you, Muhammad. And Sarah, please, can you say a little bit about yourself and also your interests and the work that we're hoping to even do more together?
My name is Sarah. I'm one of the medical students at the University of Buckingham. I've also been involved with the SSC task, and I'll be talking about that later. And I'm really interested in animals versus human health as well.
So thank you very much. So this is a kind of short introduction from us. So basically, we're going to share the latest of our work, who is going to be published, and we are hoping to encourage you today also to look into this and perhaps participate and do more. I'm also a member of the British Computer Society and the Specialist Group of AI. That's why also my call, and particularly the encouragement of use this venue in order to showcase what could be done, and perhaps even better if more people decided to join us and do more things together. So let's start. So this talk is divided into 4 parts. We are going to start with a quick overview of AI, try to distinguish clearly what is symbolic AI, what is neural AI. And then there will be particularly studies in order to go a bit depth into this. Some of the studies are going to profit from this so-called neuro-symbolic AI, and we also try to explain to you why it could be beneficial. Of course, some definitions. So I took one of them, and you see that when people try to describe, to define
Sorry, Mercedes, I think there's something wrong with your network.
There is always the mention of human intelligence. So it seems that whenever we wanted to define what artificial intelligence is, we also have a definition of what human intelligence is. So I don't know what else I can do. Let's see. It's a bit better?
Yes, a bit better.
A bit better, yes?
Yes.
Okay, so let's recapture. So a definition, as we were saying, is a bit difficult. So why, for example, natural language understanding is so hard, particularly from the machine point of view? Because as we know, the same word, a word like jaguar, can have different meanings. So it could be a car or could be an animal. When we go into the symbolic AI, it's quite famous what we call the triangle of meaning. So basically, a symbol like jaguar may evoke a concept, and this concept refers to the actual thing, that in this case, it could be either the animal or the car. When we talk about symbolic AI, we can go from weak semantics to strong semantics. So an example of weak semantics will be a list of terms or a glossary. And another example of also weak semantics will be a thesaurus. I will come back to you in a moment, which is thesaurus is normally distinguished between broader terms and narrowing terms. And then if we move in this spectrum, we will end up with strong semantics like description logic and languages like OWL. OWL is the ontology web language. Also, it's worthy to mention that symbolic AI has a very strong tradition in AI. This is the UMLS Metathesaurus, arguably the biggest in the world. You can access and use it for free. You only need to register, so it's one of these wonderful resources that is available there. It has millions of concepts and millions of terms. I will give you a latest statistics later on, one of my colleagues. And why it matters to us? Because it's UMLS included hundreds of vocabularies, clinical terminologies, and one of them is a SNOMED CT, which is the one that is encouraged to be used across NHS England. And there is also a veterinary extension of SNOMED CT. And this is symbolic AI because SNOMED CT is not only a clinical terminology, but it's also an ontology and is provided in OWL, in this description logic language.
Sorry, Mercedes, I'm sorry to interrupt. Are the slides supposed to be advancing?
So advancing is not working?
Well, the slides are not moving. It's just we're still on the opening slide.
So can you see the UMLS Metathesaurus slides?
We're just seeing this title slide, so AI in healthcare, neural AI versus symbolic AI, etc.
So can I'm going to stop sharing and I will try to do it again. Can we do that?
Okay, please.
Can you see the next slide, slide 2?
We're still on the first slide. Yes, you can see the next slide.
The number 2.
Yes.
And now the number 3,
Yes.
which is when I was talking about, about the problematic of the definitions. Then this slide is where I try to introduce why the natural language understanding is difficult, because the same word can have different meanings, like jaguar. I introduce you to what is called the triangle of meaning, like a symbol like jaguar evokes a concept, and the concept refers to the thing that could be, in this case, either the animal or the car. Under symbolic AIs, we have the weak semantics and the strong semantics, and I was trying to tell you a list of terms is weak semantics, a thesauri is weak semantics, and when you have like an ontology in OWL, which is a description logic language, that will be a strong semantics. Then I was trying to tell you about the UMLS Method Thesaurus, which is a resource that is available for free. Everybody can access and use this resource. Probably it's the biggest thesaurus for the biomedical domain in the world. And you just need to register. It doesn't cost anything, and it's just absolutely for free. Under the UMLS Method Thesaurus, you will have hundreds of vocabularies relevant or related to biohealth. And one of them, of course, is SNOMED CT. SNOMED CT is an international clinical terminology that is intended to be used across NHS England, and SNOMED CT has a veterinary extension. In a thesaurus, as we say, is weak semantics, so you will have broader and narrower concepts, like a concept like gastroenteritis. UMLS Method Thesaurus may say that a broader concept is gastrointestinal infection or disease. My colleague will talk later on about this. And here you have a typical taxonomy or hierarchy with the is-a relations. So taxonomic and anatomical knowledge is very common or very fundamental for the medical domain. And you can see here just a pictorial representation. And of course, probably some of you have heard already of FHIR data, which F means findable, accessible, interoperable, and reusable. So if you were curious, or one of the things that comes to mind when we talk about interoperable is these formal ontologies. And this is why semantics is so important here. We wanted to share knowledge, to share meaning, to know that we're talking about the same concepts. Some of my colleagues now say that perhaps we need to change this, and perhaps instead of talking about FHIR data, we need to talk about findable and reusable data for AI. But this is perhaps more an opinion than anything. And I would like to take you a short tour of different health IT standards. Some of you probably may have heard about them, and it's not casual that I incorporate them or introduce them in the part of symbolic AI. Some of them, they have been there for a substantive number of years. So, for example, FHIR is from HL7, and FHIR is typically available in 3 formats: XML, JSON, and RDF. And RDF relates to ontologies and symbolic AI. So an OWL ontology can be converted into RDF graph. And you can also say that we are talking about knowledge graphs. Perhaps the term is not so familiarized to you like other things, like ChatGPT, for example. But knowledge graphs, I can say to you that if you have ever asked Google or Alexa a question, you will have used a knowledge graphs. So this technology was underpinning commercial systems, very popular systems that they are there every day before the advent of these large language models. So just keep in mind that, for example, these standards for healthcare, yes, they're available in RDF, and this is undeniably symbolic AI. FHIR, if you go to NHS England, is one of the standards that they are pushing forwards, and there is an API and a lot of work around this in order to communicate systems across NHS. Another one is openEHR. Perhaps this is quite popular in Europe. I will say arguably some of my colleagues from Spain, for example, they are using it. And I also know people from the UK that they are working on this, or Austria or Germany or some other countries. If you're curious about openEHR, you can see here, for example, when you have a concept like blood pressure. So remember, when we talk about symbolic, there is always underlying this notion of concept, yeah, symbol concept, yeah. So you have blood pressure as a concept, and you can see here how it may relate to data, protocols, descriptions, events, or even states. And there is a paper that this is where the image was taken, so anyone interested can know more about this. Another one, arguably perhaps not so well known, perhaps it's more used in academic, in the academic realm for academics, because perhaps is simpler than the other ones, and in order to prototype things or to try things, arguably this could be more convenient. So these are like the three more popular ones. And as I say, if you wanted to say which one seems to be more relevant or pertinent for NHS England, so then once again, it will be FHIR, which stands for Fast Healthcare Interoperability Resources. And as you can see, one of the formats is RDF. So definitely symbolic is there. So what about neural AI? So large language models are deep learning models, and these are artificial neural networks, and deep learning models are machine learning models. When people talk about generative AI, this is because we are thinking about the machine learning model that is trained to create new data, more than just making a prediction. It's just creating new data. But regardless, as you can see here, LLMs are deep learning models. One of the challenges or one of the difficulties, or an area that has been extensively studied and people keep working on this, is neural AI and the black box. So machine learning models like neural networks, they are referred as black boxes because it's difficult to understand how they make the predictions. So we have an input and an output, but it's unclear how the model make these predictions. Later on, one of my colleagues will hint some possible way in order to explainability, and we are going to use symbolic AI for that. So this is another way of why symbolic could be important. So perhaps in order to help with explainability for black box, for the output of the black box, for example. When we talk about large language models, so probably you see these pictures that they are represented as circles, and the size of the circle represents the size of the model. So normally bigger circles means bigger models. So arguably 2018, 2019, this is when Google come up with BERT. And BERT, if we say when all of this started, so perhaps the public came familiarized with ChatGPT, undeniably, but if we wanted to say when all of this started, when this wave started, perhaps we need to go to BERT. So these are smaller size models. They have less than 500 million trainable parameters, and as you can see, the sizes has been increasing. So over time, the sizes of these models has increasing from millions to billions to trillions. Quite famous, OpenAI, GPT-4, and Google Gemini, which already have trillions of trainable parameters. weights in the network, if we wanted to think about this way. But they are closed model. So they are expensive and they are not publicly available. So this will lead to undeniably another impact that we have this year, which was with DeepSeek, because it's open source, it's open weight. And another interesting thing is arguably the cost was lesser than the previous models. Although if you look into articles, there is an argument about how much for real DeepSeek cost. But what is undeniable is it's open source, it's open weight, and also it can handle quite effectively this multitask. So for example, it has been one of the things that people is doing is try to compare and benchmark the different models for different tasks. And you can see that DeepSeek, despite of being cheaper and also open source, it was comparable in performance with other models like GPT-4. So perhaps this is why there has been so much talk and so much investigation about DeepSeek and the comparison with other models. As also, you know, one of the hardest things, or one of the things that is open to discussion, is what happened with data ownership. When we put data into ChatGPT or into DeepSeek, what is going to happen with this data? And this data will be seen for other parties. So we have to be careful, particularly in healthcare, because perhaps nobody wants that their own healthcare data is going to be placed in a way that we don't know who is going to access data. And this concern also arises, what we do in healthcare is suitable to use these models. So there is a lot of discussion and a lot of attempts already at legislation. To my best knowledge, in Europe, there is already some legislation about specific legislation, specific about artificial intelligence. In UK, is ongoing. So when we say that this model is better than the other, how we say that the ChatGPT is better than DeepSeek? We are based on what? So we are based on metrics, and we're interested into seeing what kind of errors they can make. So there are typically two well-known types of errors. One is the false positive, also known as type 1 error, and the other one is false negative, also known as type 2 error. And of course, considering these errors, there are also formulas, and these are the formulas that we use in order to measure the performance and being able to cross-compare models and to say, for this task, which one is better? Is ChatGPT better than DeepSeek or not? The metric will tell us. So we need some formal assessment. One thing that I wanted to make you aware, and this is one of the things that I've been pushing, and the specialist group in AI is also favoring, is trying to demonstrate that perhaps small models, open source models, can be also quite astonishing and more interesting. They can be run locally. So perhaps some of the data ownership issues just go away. So at the moment, Hugging Face, which is open source, open weight models typically, it can accomplish natural language processing tasks, computer vision tasks, audio tasks, machine translation, etc. Some of my colleagues are going to present some of these. And there is also a Python library that is, it can be used for free. So perhaps, what is the difficulty then? If the models are available and there is also code that is easy to use, so what is the difficulty? So perhaps what we want is, can we use these models for particular tasks just in 3 lines of code? So suddenly more people can do this. And what are the requirements? Perhaps we don't need a super powerful machine. Perhaps we can do this in a modest laptop, in a laptop with 16 gigabytes of RAM. We don't need to go further than that. So this is one of the things that I would like to illustrate, and I would like to show you with my colleagues what you can be done, and even propose things if you wanted to try yourself, if you're really curious. So talking about these 3 lines of code and that you can execute on Google Colab, or you can execute on your local machine. So you may wonder, well, if it is 3 lines of code, maybe it's not that useful, right? Because it's just 3 lines. So I'm a physicist. So my PhD is in physics and I study physics. So in physics, just 3 letters are useful. So I give you 3 letters from Isaac and 3 letters from Albert. So if 3 letters can be useful, perhaps 3 lines can be useful. So as you know, these formulas are very well known. One formula with the 3 letters is classical mechanics, and the other formula is relativistic mechanics. So perhaps we can do more with less. Perhaps there is a way forward, a way that more people can participate and engage and do things, not just the super powerful companies. If you're interested and curious, and if you by any chance have a Google account, this is all you need. If you have a Gmail account from Google, then you can use Colab. So typically you will have to put the file name, and you need to decide if you wanted to use CPU or GPU. And then you just put the code. And these are the examples that we are going to provide you. So you don't need to install anything, and just for trying, it could be convenient. And the same thing, of course, can be executed on your local machine. And a machine that at least 16 gigabytes of RAM, just in order to make sure that everything will be just fine. So what are these 3 lines of code? So the first line is instantiate the pipeline. So in there, you have to say, what is the task and what is the model? In the second line is the input data. What data do you want it to analyze? For example, is this an image? Is this some text? Is this an audio file? So this is where you will put your own data. And then the third line, which is showing the output of the pipeline. So under this systematization, we have been working with different examples and different tasks. And this is another thing that myself and my colleagues will show to you. So what about this task? It's an NLP task, is natural language processing task, which is called name entity recognition, that LLMs can be quite good at this, and it will be called also token classification. So this is the pipeline, and this is a Hugging Face if you're interested in using these models that I mentioned before, the 2 million models that are available for free. So in this pipeline appear the tokenizer. So why tokenizer are important? So tokenizers are processors that can encode or decode the data in a way that the model, the LLM, can understand it. So this is typically when you're going to see different examples of the 3 lines of code, and here or there, you will see some mention about the processor or the tokenizer. So for example, this, I try to give you the snippet of tests. You will see that it's quite brief. First, the requirements, what kind of libraries we need to install. Of course, this will be Python libraries, so perhaps you need to know a little bit about Python. In this case, I selected a particular model, which is the data biomedical NER-all, which is a very, very small model. So it's less than 500 million parameters, very small. So this means that it will be executed very fast. Then, as you can see in the pipeline, we say, what is the task? What is the model? In the input data, I can give a sentence, like, for example, I have a mild headache. And then in the show, the pipeline output is just showing what is the result, what are the medical entities. And as you can see here, identify mild as a B severity, and identify headache as a sign or a symptom. It is also typical of these models, as you can see, is not only give you what is the category, what is the label, let's say, but also a score. So in this case, the scores are quite high because it seems that the model is quite confident that, for example, headache score 0.999 is a symptom, is a sign or symptom. As I as I was telling you, the same code that you can execute on Google Colab, you can execute on your machine. So this is an example of just executing the code in a local machine. And yes, is quite fast for these smaller models. So what happened with instruction-based models? So there are also instruction-based models where you can provide an instruction, the prompt, that they are also medium size, we will say is a bit more bigger, but they still can be used under Google Colab and with your local machine. And in there, it's interesting because once you have certain code, you just need to modify the prompt in order to do different tasks. So for example, this you may or may not know, a model that at some point was quite reported, let's say, in academic and perhaps also industry. It was Falcon. It's 7 billion. So that's why perhaps it's important to have a computer that guarantees that it could be loaded and you can run code with it. But again, in this case, the task will be text generation. The model is Falcon 7B. And in this case, in the input data, we put directly a prompt. We put an instruction. In this case, we are not giving examples. We are just describing the task and the test, and that's it. And then, of course, the third line, as before, is just in order to show the result of the pipeline. If you're interested in this, we are going to also to propose to you different exercises, so different things that you can do exactly with this. And now I would like to hand it over to my colleague Apishan, who is going to present to you some other examples and exercises. So Apishan, whenever you're ready.
Yeah, thank you. So let's begin with some context. The world population surpassed 8 billion people in 2022. And across the globe, we speak more than 7,000 languages. That diversity of languages makes machine translation an essential tool for communication. We go to the next slide. So here's the basic idea. We use an encoder-decoder model for translation. The source language goes in as an input, and the target language comes out as an output. This architecture forms the foundation of modern translation systems. Next slide. Then let's use an open source large language model called Seamless M4T from Facebook. This model supports 101 languages for speech input, 96 languages for text input or output, and 35 languages for speech output. Let's walk through a simple text-to-text translation using symptoms of Parkinson's disease for Medline Plus. It only takes 3 lines of Python code. The first line is to encode the input. You provide the text and the source language, in this case is English. The second is the model output. You specify the target language. And the third is to decode the translated text. Next slide. We can take it a step further to text-to-speech translation, again using Seamless M4T. The 3 steps are almost the same. The input step is the same. But this time, instead of text, we ask the model to generate the Spanish speech. And the third line plays the audio output. The next slide. Here's what this looks like in Google Colab. You first have to install the Hugging Face Transformers library and loading the Seamless M4T. This model has 2.31 billion transport parameters. This process takes about a minute. Then we see text translation, which takes approximately 2 seconds, and speech generation, which takes about 4 seconds. So we're looking at using powerful models with very manageable runtimes. Okay, next slide. Now let's move from language translation to fine-tuning large language models. During my 3rd year at university, I explored how to lower the technical requirements for fine-tuning LLMs with biomedical images. Next, I'll show the recent work on customizing LLMs for biomedical image classifications. Next slide. You may wonder, what are the alternatives for fine-tuning? One option is OpenEHR platform, which allows you to train models with your own examples, but there are limitations. Only a small set of models can be fine-tuned, and the number of data samples is constrained. Next slide. For example, OpenEHR's supervised fine-tuning requires data samples. This suggests using between 50 to 100 examples, which might sound like a lot, but in practice, it's not nearly enough. So let's look at what datasets are available in the biohealth domain. Next slide. MedMist is a collection of 18 standardized datasets for 2D and 3D biomedical image classification. It covers diverse data modalities licensed under the Creative Commons, but you need ethical approval from your university before using it. Next slide. One of the smaller datasets is breast mist, based on 780 ultrasound images. At the other extreme, we have tissue mist, which has more than 236,000 samples of kidney cortex cells, grouped into 8 categories. Here's the proof of concept pipeline we developed. The 3 lines occurred before fine-tuning, and then you fine-tune your model, and after fine-tuning. In this example, we use one breast cancer ultrasound image. Before fine-tuning, the model produced irrelevant outputs, as labeled as platypus and duckbill, with a confidence score of 0.1335. But after fine-tuning, the model correctly identified the image as label 1, which represents a normal case, with a confidence score of 0.926. Next slide. Another dataset is retina mist, which contains 1,600 retina images. It was created for the Deep Grid Challenge, which focused on diabetic retinopathy. Next slide. To evaluate performance, we use metrics like accuracy and area under the ROC curve. And in fact, retina mist tends to produce the lowest accuracy and area under the curve compared to the other datasets. As you can see, the accuracy was reported at 0.53. Next slide. For this, we fine-tune a model called VitBase, which is a visual transformer, and its full name is Google VitBase Patch 16224. This is a transformer-based vision model, particularly strong on image classification. Next slide. The fine-tuning experiment takes about a minute on Google Colab and yields an accuracy of 0.58125. That's higher than the benchmark reported in MedMist. And the area under the curve is also higher than the benchmark. Now you may be wondering why did this happen? But since the benchmarks were published in 2023, it's likely that new models like vision transformers can outperform older baselines, simply by the virtue of being more recent and more advanced. Next slide. If you'd like to learn more about fine-tuning LLMs in just 3 lines of code and their relevance to neuro-symbolic AI, I would like to invite you to the face-to-face event at the BCS London office in November. Thank you.
Thank you, Abhishan. I would like to introduce our next speaker. So Mohammed is going to explain some of the work we have been doing. So please, Mohammed.
Hi, my name is Mohammed Walid Iqbal. So I'll be going through, briefly going through this presentation about how artificial intelligence is changing medicine. So just a brief introduction, ChatGPT was publicly released on 30th of November 2022, and it's quickly gained global attention due to its ability to generate human-like texts. So its release sparked discussions across industries, including healthcare, education, and research, because it can perform tasks like drafting emails, summarizing medical literature, and even assisting in coding. It's something we'll mention later on as well. Next slide, please. So OpenAI of ChatGPT, so OpenAI's ChatGPT is a large language model trained on vast amounts of text data. From a healthcare perspective, this means that it can help clinicians quickly summarize research, draft patient information leaflets, or support decision making, though it's not a substitute for clinical judgment. In the study that I'm presenting, we compared 2 points in time, before and after the introduction of ChatGPT. This approach allows us to understand how the availability of such AI tools might influence medical practice, research productivity, and even educational outcomes. So these 2 time periods are before 2021, before the advent of ChatGPT, and April to July 2025. Next slide, please. So as mentioned before, I'm a medical student from University of Buckingham, and I'm a co-author of this paper that will be presented at the AI 2025 International Conference in Cambridge this year. So this study was mainly aimed to provide insights into, one, what information sources are used by clinicians to support their clinical practice, 2, questions raised by clinicians at the point of care, and AI in healthcare before and after the advent of ChatGPT. Next slide, please. So let's review some of the essential notions for this study. This is a action research study which engaged clinicians as collaborators rather than subjects, using a mixed methods approach that combined qualitative interviews with quantitative self-administered questionnaires. For analysis, we used thematic analysis, identifying themes both at semantic level, looking at what was explicitly said, and at a latent level, interpreting underlying meanings. To ensure reliability, external auditors reviewed the process following consensual qualitative research standards. Next slide, please. So you can see here that the clinician's title for the 38 participants that we had, 32 of them were junior doctors, one of them nurse practitioner, and 5 medical students. This is an action research, and it has 3 important elements: participation, democratization, and contribution to social science and social change. Next slide, please. So in 2021, before the arrival of ChatGPT, the interview data of 17 clinicians from the UK, this is number P1 to P17, was segmented. This slide shows the kind of clinical questions that the 17 UK clinicians were asking in 2021 before ChatGPT. We classified their questions into a taxonomy of types. The most frequent questions were about drug treatment, particularly dosage, drugs of choice, and how to maintain conditions overall. Less common were questions about causes of symptoms or test findings or about risk factors. This just shows that the clinicians often turn to information sources for very practical treatment-related queries rather than purely diagnostic reasoning. This will come important later on. More importantly, each question over here was given a taxonomy code. And sorry, can you move to the next slide, please? So you can see here some examples of question types. So this table is a thematic analysis output showing codes and sub-themes for the kinds of clinical questions that the clinicians asked in the interviews. The analysis looked at both semantic and latent levels, meaning it just didn't capture only the literal question, but the deeper meaning behind it. You can see the questions covered a wide range, from interpreting X-rays and blood results to deciding on drug treatment like remdesivir, which is for COVID-19. There are more COVID-19 related queries here highlighted because of the pandemic at the time. The key point here is that the clinician's information needs were diverse, spanning diagnosis, treatment, investigations, and long-term management. Next slide, please. So this is, as mentioned before, the study considered 2 points in time. We've grouped them 2 together. So from March 2020 to February 2021, this is before ChatGPT, it's mentioned as grouped as 2021. And then April to July 2025, which is after the ChatGPT and DeepSeek R1, which is named 2025. Here you can see some sub-themes that we developed under the theme designated as T1, what information sources. These show the range of tools and references that the clinicians reported using in practice. Next slide, please. So just a continuation of the last one. Here you can see some more of the sub-themes in that clinicians mentioned. This highlights the diversity of sources that were being used to support decision-making at the time, from more traditional resources such as the hospital guidelines, as well as to some of the newer digital options as well. And next slide, please. So this study paid special attention to the codes developed for the sub-themes with the type online sources, given their rapid growth in clinical use. You can see here from examples of websites and apps used by clinicians. For instance, there's pediatric emergency apps, there's online clinical libraries and radiology platforms like Radiopedia. These tools are becoming increasingly integrated into everyday practice. Next slide, please. So you can see some more examples of websites and apps clinicians reported. There are quite a lot. You can also see some here wiki-based resources as well, such as Radiopedia, Wikipedia, and iWiki. This just highlights how clinicians often cross-reference their open access resources alongside the formal clinical tools that's available throughout the hospitals. Next slide, please. So these last two roles were added in 2025 as new subteams to investigate ChatGPT and its alternatives such as DeepSeek, Grok 3, Beta, and Claude as well. And this slide is central to our findings. So by 2025, approximately 3 years after its release, ChatGPT itself was mentioned by 12 UK clinicians, and alternatives such as DeepSeek, Gemini, and Claude also appeared. In the UK responses, ChatGPT was explicitly reported as being used for rapid information, while alternatives like Gemini and Copilot were also explored by smaller groups, and not as common as ChatGPT. From the Australian replies, ChatGPT again appeared multiple times, but the interesting thing was that they also used some local AI tools such as Lyrebird AI and Manus AI. So the big shift is not only the adoption of AI tools, but the emergence of a range of competing AI platforms, showing that clinicians are actively trialing which ones work best for them. Next slide, please. So in conclusion, cross-comparing 2021 and 2025 clinician replies, it becomes quite clear that between 2021 and 25, we see a clear rise in the online resource use, expanding beyond just medical libraries to include wikis and AI tools. At the same time, clinicians are increasingly using Google's searches and ChatGPT, but there's a recurring concern. While these tools are quick and accessible, they are less reliable for complex and nuanced diagnostic cases. This tension between accessibility and accuracy is key to understand how AI is leading change in medicine. So just to the last concluding remark, next slide, please. While AI tools tools like ChatGPT show great promise in supporting clinicians and enhancing patient care, there is further research that's needed. It's quite essential. We need a comprehensive understanding of which information sources truly add value at the point of care and how AI can safely and effectively be integrated into everyday clinical practice. That's it for me. Thank you very much.
Thank you, Mohammed. Sarah, please, would you introduce the next study, please?
I'm Sarah, I'm one of the medical students at University of Buckingham, as I've already told you. So I'll be doing this next part on human health that doesn't exist just in isolation. So according to the World Health Organization, 60% of emerging infectious diseases affect humans and originate from animals, so both wild and domestic. The statistics isn't just epidemiological data, it's also clinical reality that impacts our practice as doctors. Some recent examples include obviously COVID, which is likely zoonotic in origin, and influenza from birds and monkeypox from rodents. So understanding the zoonotic transmission patterns is crucial for different diagnosis and outbreak investigation and preventative medicine. Next slide, please. Thank you. The symptoms we recognize in human patients often mirror those in animal populations. So our research analysed 2.5 million veterinary records alongside human clinical data from MIMIC3, which showed striking similarities in symptoms, in symptom presentation and clinical documentation patterns. So the most key finding was clinical terms such as in the bigrams, trigrams, and quadrigrams that overlap. They overlap significantly between human and veterinary medicine, particularly in results, i.e. like lab values, diagnostic findings, healthcare activities, so procedures, treatments, and anatomical locations, so body systems affected. So the clinical relevance to all this is that it suggests that monitoring animal health could provide early warning systems for human disease outbreaks, which is, always a good thing. So if we examine a clinical scenario for human, oh no, is it okay if we go back a slide, please?
Yes. Sorry.
Thank you. Yes. Thank you. So if a human patient presents with nausea, vomiting, and mild fever, so mild fever we mean like 38.2 degrees centigrade, we have differential diagnoses. So that would be viral gastroenteritis, food poisoning, and early appendicitis. But then also in veterinary medicine, it would be dogs with gastroenteritis present with vomiting and low-grade fever. So a normal canine temperature would be 38.3 to 39.2 degrees Celsius versus humans, which is 36.5 to 37.5 degrees Celsius. The One Health application would be if multiple pets in an area show similar GI symptoms. This could indicate environmental contamination, so water or food sources being contaminated, zoonotic pathogen emergencies, and need for enhanced surveillance in human populations. Is it okay if we go back a slide? I'm so sorry. Perfect, thank you. So accurate symptom documentations is crucial for both human and veterinary medicine. So the temperature detection challenges. Is it possible that we can maybe go back a slide again? I'm so sorry. Yes, perfect, thank you. Vomiting, it can be quite ambiguous. There's an abbreviation ambiguity. So T doesn't always mean temperature, and V doesn't always mean vomiting. If we go forward one slide, sorry. And again, sorry. There we go. So vomiting, the shorthand V could mean very or vomiting. And then also there's spelling errors in clinical notes. Doctors are notorious for this. There's also context matters, so the patient vomited versus no vomiting reported. And then if we go forward one slide again, please. There's also temperature ambiguities. So T doesn't always mean temperature. And then there's multiple terminologies, fever, pyrexia, and temperature elevation and hypothermia. There's also negation detection. So say if like a patient says, patient denies fever versus patient has a fever. So a missed or misinterpreted symptoms can delay diagnosis and treatment, particularly in zoonotic disease outbreaks. So if we kind of standardize the medical terminology, the unified medical language system helps us overcome terminology barriers. So the UMLS meta-thesaurus links alternative medical terms to standardized concepts. So for fever, there'll be temperature elevation, pyrexia, hypothermia, and febrile state. And what this will help with the clinical bit would be it would improve interprofessional communication, clinical decision support systems, and research data integration, and also will help the One Health surveillance system as a whole. Next slide, please. Perfect, thank you. So we created a computer tool that can read doctors' notes in many different ways and automatically spot important symptoms. So for example, when doctors write about the same symptoms in many different ways, the patient has a fever versus temperature is 38.2 degrees Celsius versus febrile versus pyrexic. A computer needs to recognize all of these things mean the same thing. So our solution is a 3-step process. Is it okay if we go? Thank you, perfect. Medical dictionary lookup. Used to establish medical vocabularies to find all possible ways to write about fever and vomiting. So this will be basically just a dictionary, and expert validation in step 2. So we would have practicing clinicians review our list to make sure we didn't miss any common abbreviations or terms. And we would also create a rule where clear instructions for the computer, like if you see temperature and a number, that's a temperature reading. And if you see no vomiting, or that means like patient is not vomiting. So why does this matter? This computer system can quickly scan through thousands of patient records for symptom patterns. It can help identify disease outbreaks early, and it saves doctors time in reviewing large amounts of clinical data. So if on the next slide, perfect. Our data shows the performance is over 90% accuracy, and it's as good as a human reviewer. And as physicians, we need to understand why our tools make a certain decisions. So we need based approach benefits. So transparency, we can see exactly why that decision was made, and then interpretability, clinical logic is preserved and auditable. You can just see what everything is going on. Then there's also healthcare providers can verify AI recommendations, so adding that extra layer of trust. So, for example, of clinical explanations, so temperature over here, 30 is 38.2. So that's an observation, okay? So that means the system detects a fever measurement. The next one is the explanation of vomiting and vomit/vomiting. So the system correctly identifies denied symptoms. So why does this matter? In clinical practice, we must always be able to explain our diagnostic reasoning to patients, colleagues, and regulatory bodies, or else we'll get in trouble. Next slide, please. Thank you. Why do we need reliable clinical AI? So different AI systems can interpret the same patient notes differently, which can affect patient care quite drastically. So why is this a problem? We gave the same clinical text to two different AI systems, both ChatGPT and GPT-4 and DeepSeek R1. So one focused on abbreviation vomit and temperature. The other focused on complete phrases such as fresh blood and vomit, and they labeled the same symptoms differently. This inconsistent AI could lead to misdiagnoses or incorrect coding. So we need AI systems specifically trained for medical use, not just something that's out on the internet generically. Next slide, please. So we built AI tools specifically designed to detect fever mentions in clinical notes. So what we did was we collected 1,505 sentences from real patient consultations and had medical experts label which sentence mentioned fever/temperature. And then we trained 7 different AI models to automatically detect fever mentions. So the result was best accuracy was 98.74, which only missed 1 to 2 cases out of 100, which is really good. And the training time it took was just over a minute, and it works just as well as human experts. So doctors could use this quickly to scan patient records for fever patterns across populations, which is such a crucial find. Next slide, please. And we achieved the same high accuracy for detecting vomiting or nausea in clinical notes. So it's the same process, just different symptoms. So 1,743 sentences were scanned about vomiting and nausea, and this showed a accuracy of 97.67%, which is also like around 1 minute training time. So during a gastroenteritis outbreak, if that were to occur, like it did during COVID with the coughing epidemic almost, this tool could rapidly scan all patient records to identify cases and track their spread, which is quite useful in an outbreak situation. Next slide, please. So, to conclude, our research demonstrates a practical neurosymbiotic approach to One Health medicine. So what are the key kind of takeaways for medical practitioners? Data privacy and ethics. Local deployment avoids patient data sharing concerns. So we don't want to get into trouble with any authorities around sharing data or anything. And it also maintains compliance with healthcare privacy regulations. The second point is neurosymbiotic AI benefits combines rule-based transparency with neural network performance. So this provides explainable predictions for clinical decision-making, and it's almost like a guideline. It also enables rapid customization for specific medical applications, which is always good. There's also One Health applications, so cross-species symptoms monitoring for outbreak detection, integration of human and veterinary health science surveillance, and enhanced preparedness for zoonotic disease emergence. So where can we take this in the future? Next slide, please. Implementation in electronic health records. There's also real-time syndromic surveillance systems and clinical decisions support for infectious disease management. So we could basically, we have a responsibility to embrace technologies that can improve patient care whilst maintaining the highest standards of medical ethics and clinical judgment. Thank you.
So thank you very much, Sarah. So we enter into the last minute, let's say, which is based on what my colleagues have already showed you. I'm just going to go quickly again, just in order to pin down the differences. And one of the differences you may observe is when we give information to a ChatGPT or some other large language model and we ask for the category, perhaps we can notice differences. But more importantly, are these categories the same or closely to what NHS England, for example, is encouraged to use, which is, for example, SNOMED CT? What are the differences? And this is what I'm going to try to pin down in the next minute. So as you all know, menopause is if women live long enough, is one of the conditions, and women represent half of the population. So a BMJ-based practice about menopause try to give hints about what is the clinical presentation, what are the symptoms for menopause. Among them is mood changes. So if we take mood changes, and as we can see here, this is just tests. So typically, and this is one of the things that we need to keep in mind all the time, for NLP, traditional, what it tried to move is from unstructured data to structured data. And an example of structured data we saw before is SNOMED CT. So if we take this paragraph from, or this snippet of text from BMJ best practice, we can identify, or doctors can identify immediately, like third-time concepts. And in a SNOMED CT, they will be represented and they will have a particular code. So we remove ambiguity. So they identify by a particular code and by a concept name, and different alternative names could be possible. And the category, which is quite interested in this case, is clinical finding, or finding for short. But what about neural networks? So if we ask them to do token classification, which is for the same test, try to identify the medical entities there, we can write a prompt, like you're a medical expert, and identify and classify the name entities in the very same test that we saw before. And we can see different models how we go about it. So for example, Gemini will identify mood changes, irritability, mood swings, sadness, and crying for no reason. And the category will be symptom or sign. If we go to other model like Grok, it will identify them as well, but the category will be symptom or medical condition, which is peculiar. If we go to Claude, it's going to say that mood changes, irritability, mood swings, sadness, and crying for no reasons are psychological symptoms. If we go to another model like Roxy, it's going to say medical symptom, and DeepSeek, for example, will say that it's medical condition symptom for mood change, irritability, mood swings, sadness, and crying for no reason. So even if you can argue that all of these large language models can identify the medical entities the same as, for example, a doctor, a junior doctor, there is differences in the kind of labels, the kind of categories that they are saying, and none of them, quite interesting, was able to say clinical finding, which is in a way what we expected, because in a terminology like a SNOMED CT, all of them will be clinical finding. However, as you can see, none of them, not Gemini, no Grok, no Claude, no Grok 3, no DeepSeek, no ChatGPT, nor OpenMax could say this clinical finding. If you're curious about the small size biomedical large language models, that they are super fast to execute, and as we say, this relates to the work that we have been doing about the 3 lines of code. In this case, the smaller models are now instruction-based, so you have to provide the input and it will provide the output. What are the entities recognized there? And we can see mood changes, irritability, mood, sadness, crying. Perhaps there is a split very clear between crying and crying for no reason. However, the small is very small and it's a model that you can run locally. So perhaps it's worth it to try to investigate how the two fields, symbolic AI and neuro-symbolic, can contribute more and can inform more each other. And again, if you're interested in knowing more about this or doing yourself a little bit about this, so I invite you to this face-to-face in London in November, where we can talk even with some of the presenters here and try to bring perhaps some of your examples if you want. Now we are open for questions, but as a curiosity, I would like to propose 2 exercise, let's say, or something for you to consider. One is from symbolic AI, like if someone gives you all of these different terms, how you can classify them. Can you come up with some categorization? Can you come up with some taxonomy for them? Or this other one, which is about neural, which is considering the different prompt techniques. One of the ones we saw here, it was a few shot, but there is also, zero shot, but there is also few shot and change of thought prompting. And of course, you can do this programmatically, as we say before. So this is the example that we were providing before about the zero shot, but you can also do the other examples. And this is, for example, using exactly the same line of code, but in this case, doing a more sentiment analysis. So if anyone is interested in this, again, please come to London and we can show you how you can do this. I mean, programmatically, this will be the reply to some of these exercises. The exercises are also becoming available. So if someone is curious, or if you're curious to execute some of this code exactly yourself and see the results, please come along. And that will be all from me. I think this is time for questions. So thank you very much for attending.
Thank you very much, Mercedes. And thank you, Apishan, Mohammed, and Sarah as well. Really appreciate this. Any questions? Any questions for the team? All right, very interesting presentation. I'm just wondering, Mercedes, you know the three line system you're proposing. So what's underneath these 3 lines? What was the engine?
So you need an environment where you can execute the code, and that's why we were proposing, for example, Google Colab. That means if you're not interested in installing anything, you don't need to. So if you allow me, I'm going to put one of the slides, which is, for example, this one, yeah? Yes. So typically, if you work with Python, you will need to install some libraries. This you do just once. So if you try to run this code in Colab, it will be exactly the same as in your local machine. You start installing and loading certain libraries that you need to use. Then what we call the first line of code is because we realized that Hugging Face has 2 million models. But if you look into the code that is needed to use them, to execute the code, you will see quite a lot of variance. So sometimes you will have half a page, sometimes you will have less than that. And there is not a systematic way in order to execute different models. So we were curious, like, can we execute different models for different tasks? And the task could be natural language processing or image recognition or voice recognition. So dealing with different event types of data, but the way that you go about it is exactly in the same way. So pipeline, this is from the Transformers library that is also available for free through Hugging Face. So executing this code, for example, in Colab, if you have a Gmail account, is for free. If you have a computer, hopefully with 16 gigabytes of memory, perhaps you will need a bit of help from someone in order to install some of these Python libraries. But again, IT services, normally through your university or company, perhaps can help you with that, and you do it just once. And after that, it's just a question of trying different tasks with different data, etc., with the benefit that you will run this locally. As we saw before, this could be, what if we can do more or less the same thing that we can do with ChatGPT, but locally? This was our curiosity. Can we do the performance? Perhaps it's not going to be equally high, but perhaps it's not so low. That's why, for example, we were working also with fine-tuning, which is customizing some models for particular tasks. And as we try to demonstrate, it could be a minute. So perhaps we need to open a discussion about, they talk about sustainability and what is the cost of using AI or implementing AI. So we argue that it's not millions and not even thousands, but we still need to work on what is the knowledge, what we need to know about this. So as your question was very right, we need to know that perhaps we need to install something, yeah?
Yes.
And perhaps we need someone who help us a little bit with this IT part. But as you can see here, even the installing is just 3 lines. So yeah, it doesn't look like, oh, I have to install hundreds of libraries. No, it's basically transformers. Yeah, and perhaps a torch and some other things, but not so many things. Yeah. And then again, pipeline is already from Hugging Face, and they already did a good job. Like you say, the task could be text generation. For example, if you're going to use instruction-based models like Falcon. And then, yes, there is always a little bit of technical knowledge. So that's why we try to provide as much examples as possible that people just copy and paste, let's say, and they just put there the text they want, or the image they want, or the audio file they want. And the only thing missing is, can we repeat this quickly 100 times or 1,000 times? And suddenly all your data could be analyzed. Because in here you can see just one line, but there is nothing to stop us to do continuously with much more information. If you can analyze one image, hopefully you can analyze hundreds. It's just a question of repeating the process. But it's the process itself what we are trying to simplify, so more people can have access to this and more people can try even in their own computer. So can we, instead of going to the ChatGPT webpage, can we try to run ourselves just 3 lines and see how it goes? If you allow me to go to what Apishan was presenting, one of my colleagues. So 34. You know that at the moment, NHS England is pushing forward, like when you doctor see a patient, perhaps there is some recording in place and generating what has happening during this process. But there are models available for free, like my colleague was presenting one from Facebook, but it's open source, so it's available to everybody. And it can translate to a certain extent medical text. Of course, if you fine-tune them, if you customize this model, it can do even better. But this is what we were trying to say, that even translate some text into some other, like you have a patient and perhaps language is not the first language. Can I just quickly try to give them, you know, the same information, but in other language? I mean, the applications are endless. The only discussion that we need to open perhaps is, do we need, you know, super large language models, or perhaps some level of customization with smaller models could be useful and more affordable. They can run quickly, and it's also less investment of money. But I'm afraid, I don't know about you, but I'm afraid that not many people know that there are 2 million models available for free, with libraries available for free in an environment that you can run for free or even on your computer. And perhaps this is the message that we can to deliver, that we would like to deliver, that more people can engage with this. And I was lucky enough to engage with computer science students, but also with medical students. And perhaps the question will be for them, because they also run the code. So Muhammad and Sarah, can you comment, please? It was super hard to run this code, or could you do it? Can you say something, please? Mukhtar, sorry, Mohammed or Sarah, please.
Yeah, I mean, we didn't have much background in in coding and stuff, but it was still pretty easy after getting like an introduction lecture to run something like that. I know more colleagues as well who are also looking into something similar because of AI becoming so popular in like healthcare environments these days.
Sarah, do you have some comment to offer?
Really easy to use, especially with like Mercedes like guiding us all through it. I think everybody in the class, especially, we were able to just do it quite quickly as well. It was quite intuitive too, but yeah.
Abhishan, you were working on the hardest, which is the fine-tuning. That Sarah, let me go to that one. Sarah tried to say, how super fast. So let me go and find the slides. So for example, fine-tuning tests. I mean, Abhishan demonstrate fine-tuning images. Sarah just provide an example about what about fine-tuning tests. But Abhishan, perhaps you would like to say something about your work, because Abhishan is trying to also provide the 3 lines of code for fine-tuning audio. Abhishan, can you get some insights into what you're doing? I mean, it's ongoing, but can you share a little bit with us?
Yeah, so basically, the 3 lines of code has like a lot more in the background. So basically, the first line is just processing everything. So it might just seem like just 1 line of code, but in the background, there's a lot more lines of code, and it just processes everything. So it's like processes the same, and so on, like converts it to like the right audio file format, and so on. So there's just a lot more happening in the background when you're under code.
So basically, what we're trying to see is how to move from the 3 lines of code to use a particular model, to use 3 lines of code to fine-tune, to customize a particular model with some data that you may have. And of course, ideally, perhaps you wanted to have your data on your own computer, and you wanted to do this on your own computer because you don't want to share the data, or it's just experimental. Yeah, I mean, or if it is a company, you wanted to do it under the umbrella of the company. So perhaps you don't want to use Google Colabs or some other thing. So what we're trying to showcase is how to do that. So if you allow me just to go back to the very end, I will encourage people who wanted to know more about this, and perhaps they even have particular examples or something, to come back to London. So let me put the... So this will be my message. If some of you are interested or wanted to know more, or perhaps you have an intriguing example that you would like to have some, please come to London, because there will be time and space in order to talk, and perhaps we can do more together. We're just trying to provide as much examples as possible. We have already around 32, and we are hoping to release this also available to everybody. So whoever is curious and wanted to try, why not? I mean, trying to facilitate this. I don't know if anybody has any other question, but as I say, we will be delighted to answer questions, and even face-to-face questions, even better, for someone who is interested.
All right. Thank you very much, Mercedes, and thank you, Abhishan, Mohammed, and Sarah. Please, let's appreciate them with another round of applause. All right. Thank you to everyone who's attended this. Our next our October meeting will be joining with Leicester. We'll join Leicester branch for the October meeting, and this will be on Monday the 13th of October 2025, and the topic is protecting intellectual property. I hope to see you and others there. Take care and have a lovely evening.